and then sometimes you have the time. Okay. Okay, I'll start. So this is the last and the fourth and the last lecture on algebraic number theory. So we'll start by recalling where we ended last time. So we're somehow at the end we're computing the ideal class group of a particular ring of integer, namely Q adjoint square root of -14. Okay, so let's recall this. In this case, OF is D adjoint square root of -14, and then Minkowski bound. In this case, equal to square root of 56. This is the absolute value of the discriminant times a 4 over pi to the 1 for the complex embedding times another factor, which is 2 factorial over 2 to the 2. So these are degrees. So these three 2's, they are degrees. And you punch into the calculator, you get around 4 times 7, 6. So the result is it suffices to look at factorizations of primes equals 2 and 3, or sort of any number that's smaller than this one. 4 is 4 is 2, so doesn't really matter. Okay, so now let's recall that 2 factors at 2 comma square root of -14 squared, and 3 factors as 3 comma this plus 1 and 3 comma. Okay, so these ideals factorization. So the goal is to prove that the ideal class group of OF is a cyclic group of order 4. So basically, the 4 element will be represented by the principal ideals, the ideal class of 1, and this ideal class of this 2 comma root of -14, and these 2 ideals here. So what we'll show is that first of all, this ideal 2 comma root of -14, root of -14, that's not a principal ideal. It's not a principal ideal. And therefore, it will represent a non-trivial element in the class group order 2. Secondly, this element I will show that it represents an element of order 4 in the group. So in a cyclic group, so that really means that I want to show that if I square this element, so that's the same ideal class of this ideal class which has order 2. In the group of order 4, you square the element with order 4, you get the element of order 2. Let's do the 2 steps. Okay. So these are just boils down to some sort of explicit calculation, which we do now. So for 1, suppose not. Suppose this ideal 2 comma root of -14 is principal for some alpha in Z. Okay? So this is sort of a typical argument you use in the case of imaginary quadratic field. What you look at is you take the norm of the ideal. On this side, you get the norm of the ideal generated by alpha. And we said that if it's a principal ideal, that's just basically just the usual norm of an element. Of course, it's better to add absolute value, but in this case, actually, the norm is always positive, so you don't have to add absolute value. Okay. So now I have to explain what's the norm of the first ideal, 2 comma root of negative 14. But you kind of see this from here. Via this factorization, you know that the norm of 2 comma 14, if you square that, remember the norm is multiplicative, so therefore that's the same as norm of the ideal generated by 2. And that's just basically the norm of the number 2. The 2 under 2 embeddings are just both back to 2. So you get 2 times 2, which is 4. And therefore, this norm is 2. Okay, 2 comma negative 14, sorry. So this is ideal 2. So the norm of the ideal 2 comma root of negative 14 is just 2, because the square of the norm is 4. On the other hand, this equals to the actual norm of this alpha. Let's assume this alpha looks like, too low. So let's assume this alpha looks like a plus b times root of negative 14. Then if you take the norm of this, it's going to be a plus b root of negative 14, and its complex conjugates. And this is the same as a squared plus 14b squared. Now you see that you have some equation which looks like 2 equals a squared plus 14b squared. There's no solution. There's no integer solution. No integer solution. I mean, 2 is not a square plus 14 times another square, obviously. No solution. So that implies that this is not a principal. Basically, for imaginary quadratic field, for ideal, if you want to show some ideal is not a principal ideal, the best way is to show that, just take the norm and show that the norm, there's no element of that norm. That's usually somehow the case. Okay? So let's do the other one. Do the other. That looks a little bit scary. It's okay. It's okay. So I want to do something slightly different. So you want to show that, you're in an order 4 group, right? You want to show the square of the order 4 element is equal to the order 2 element. You want to show this, and that's equivalent to show that if you multiply this thing with this, you get the principal ideal class. That's the same thing because this guy has order 2. If you want to show something is equal to that, it's equivalent to show that that thing times it is equal to 0. Because again, this ideal class is the same as its inverse. So now it's just a plain calculation. Stretch. What's a good way? There's no good way. Let's do it. It's not a pretty part of dark. Let me see. So okay. Well, okay. Let me do the square first. Square is that, remember that even if you square an ideal, it's not square, you don't just take the square of the generators. You have to take pairwise product of the generators. So you have 9 here, you have their product 3 times, let me just write 3 plus 3 root of negative 14, and the square of this one. So that's negative 13 plus 2 times I mean, not the prettiest number you've seen, but then I'm trying to decide whether I just want to take another product or. Let me simplify a little bit as I have in the notes, maybe. So, okay, so when you have these two, if you have two elements in the ID, you can take their difference as you wish. So I can take the difference. So let this one to subtract the third one from the second one. So I get 16 plus root of negative 14 in there. And now I can, when I have 9 in this, I can probably get negative 2. I mean, basically the idea is you want to get some number looks smaller. That has a better chance to be the generator. Okay? So now I want to say, okay, this element, so let me just write it down here. So you definitely have 9 here, and negative 2 plus root of negative 14. You definitely have these two here. And I want to say that when you have these two, you can forget about the more complicated ones. Let's maybe just do this calculation in your head. So if you multiply this one by 2, you get negative 4 plus 2 times root of negative 14. And over here you have negative 13 plus 2 times root of negative 14. So their difference is negative 9, which is this first factor here. I'm not sure if I want to write that part. So this part you have the negative 13 plus 2. Let's equal to negative 9 plus 2 times. And same for the other one. That's equal to, well, you have 3 times this. Probably add another 9, you get this one. You can guess, it shouldn't be too complicated. Okay, so you have this. So basically you use this thing and simplify things to a very relatively small coefficient number, and you kind of just guess that that number will generate back everything. And over here, you're not supposed to get it principal ideal because you know that you're just squaring this, and you're squaring an element in the degree 4 group, order 4 group. You should not get the identity element in the ID class group. So therefore, whatever you're getting here should not be principal. The next step, you're going to get principal ID.
Did you multiply all 4 of the elements together? I only see 3 products.
Oh yeah, because it's square. You do AB equals BI. It's supposed to be 4. Right, over here you have square, like AB square is equal to A square. So well, suppose it should be AB, B, and B square, right?
Yeah.
These are really the same thing. So that's why you have 3.
Got it.
The next one will have 4. Yes, the next one will have 4. Not that I like that very much. Well, I guess this isn't why. What's this? Okay, and what's the good way? Okay, using these two, you multiply this by 4, and then subtract 4 times that from this, you get 16 plus that. And using these two, you really get negative 2 plus. So basically, let me just say it. At the end of the day, after a long discussion, you realize this is a principal ideal generated by negative 2 plus root of negative 4. Okay? I guess this is one way to kind of see by brutal computation. If you're not happy with this sort of this complicated computation, you may be able to kind of know ahead of time what you might be getting. So here's what you do. You take the norm and see what happens. Right, I mean, let's just go back to here of the factorization. So this one has norm 4. This one has norm 9, right? And that means basically this factor has norm 2, and each one of these will have norm 3. I think that's something you probably expect anyways. And so therefore, over here, when we do this computation, the norm would be 3 squared times 2, which is equal to 18. And if the claim were true, this 18 will be a principal ideal, right? So this would be equal to, I mean, how do we do the principal ideal here? A principal ideal will look like something like a squared plus, the norm of a principal ideal should be a squared plus 14b squared. This should be a squared plus 14b squared. So you can probably guess ahead of time that the generator would be, so whatever computation n will be either equal to, so I would guess either negative 4 plus root 14 or 2 plus root 14. Of course, I don't know which one I will be getting, but probably one of the two. So this will help, maybe, at least psychologically support you to go through the computation. And also at the same time, check for any sort of potential sort of mistakes. I guess, for example, here, when you compute the square of this one, you see a negative 2 plus root 2 negative 14. That's somehow a good psychological support. We're getting in the right direction. Just keep doing it. You see something that looks like what you're going to get at the end. Yes?
How did you make that guess?
What guess?
When you're like, oh, it's either...
we just solve this. 18 equals a squared plus 14b squared.
Oh, there.
I mean, think about it, like if b can't be 0, right? B can't be too large. The best is b equals 1. If b is 2, that will be at least 450 something. Too large. So b has to be plus minus 1. So a, in that case, just plus minus 2. The signs doesn't really, like you can have plus minus. And, for ideal generation, it will be the same thing. So two things. So these are probably something you're going to end up with. Okay? It's a bit of computation though. Yes?
How do you know it's cyclic and not like Z2 cross Z2?
That's a very good question. So maybe starting from here. So how do you know it's? Actually, I don't know. So basically by guessing. So first of all, when you look at this situation, right? So here's how I would think about it. Look at the situation. You have something squared equals to principal. So the first question I want to think is that an element of order? Is that a principal ideal or element of order 2? Right? So that boils down to the question whether there's an element of the norm 2. And clearly there's no element of the norm 2 because a squared plus 14b squared can't be 2. So that's definitely an element of order 2. Now, I have some additional things I have to consider. These two. And obviously these are not principal because same argument. A squared plus 14 squared b squared cannot be 3. So now you want to square it. If you think of, can the square be a principal ideal? So you ask whether this could be a principal ideal or not. Well, first of all, it's very unlikely it's going to be the same as 3 because 3 factors this and this ideal doesn't look like this one. Okay? And it could be some other crazy, generated by some other crazy algebraic integers. Well, again, you look at this a squared plus 14b squared. It can't be equal to 9 either, except unless a equals 3 and b equals 0. If b, there's no other possibility. So if it were a principal ideal, it would have to be 3. Right? I mean, it's not that difficult to show that it's actually not the ideal generated by 3. So you know that this is not going to be principal. So I guess, if you look at group of order smaller than or equal to 4, there are not many options. And you also have an element of order 2. So basically, you're only choosing between single group order 4 and Z mod 2 plus Z mod 2.
Yeah.
Also, this one square is not a principal ideal. So Z mod 2.
That's why I was asking how. That was pretty much my question.
Yeah. If the group is a bit larger, like somewhere around the size of 10, I think I would just give up. Ask Sage. Yes. Sorry, not give up. Ask Sage. Compute the class group for me, please.
Make the computer program do it for you.
Yes. That's why we have Sage. Or we could do other subject of mathematics. Just give up. Okay? Good? what do you think of cases of the problem? Telling people not to study number theory. Okay, so now we've talked about the ideal class group. Now I want to talk about another very important arithmetic information about the ring of integers. Then like the units in here. We're going to define it. So this is all the elements in OF such that you can find another element. You have multiplicative inverse. So basically, you can find a multiplicative inverse. You can invert it. Okay? And I'm going to prove this in a minute. So that's the same as element in the ring of integers and its norm being plus or minus 1. This may be another way to see it. Okay? Let's check this. If I have an algebraic integer such that uv equals 1, then I can take the norm of both sides. But the norm of algebraic integer, they're all integers. Yeah. So when you have two integers multiplied to 1, they better be plus or minus 1. So norm of u must be 1. Oh, sorry, this is really terrible writing. Why did I write this? Number cannot be equal to both 1 and negative 1. Okay? So, I mean, conversely, you can sort of do the same thing. I guess I don't have enough information. Anyway, so conversely, what you want to do is you want to know that norm of u is plus or minus 1. Then what you note is that somehow the norm of u, divided by u. First of all, this is a product of all other embeddings. This will be an algebraic integer in the algebraic closure, because this is a product of all the other embeddings of the algebraic integer. And on the other hand, it belongs to f cross, because this is just 1 over u. 1 over u always exists in f. So the fact that if you take an algebraic integer, whether it's in the same field or not, if it's in the field, then it's automatically belongs to OF. So plus minus 1. So therefore, somehow the inverse of u actually lives in OF.
Wait, why did you say it had to be algebraic integer?
Because it's equal. Because the norm of u is equal to the product other tau 2 of u, tau n of
The
u.
conjugates.
Yeah, conjugate. These are all algebraic integers.
Okay. Yeah, because they have the same minimal polynomial.
Yeah, they have the same minimum polynomial. That's right. I know, but of course you don't know whether each one of them is going to be in f. But their product is, because the product is 1 over u, or plus minus 1 over u. So it's both an algebraic integer and in f. So therefore, it's in all of that. So this is equivalent description of the structure of OF cross. Okay. So the following might be a little bit abstract, but anyways, I'll state first the theorem, and I'll explain how to understand the theorem and why this is. I guess I'll give the application of the theorem in a bit. Give a structure of this one. So say f has R1 real embeddings and R2 pairs of complex embeddings. Then the theorem of Dirichlet, a Dirichlet unit theorem, says that the group OF cross is finitely generated, first of all. With you can find at most R1 plus R2 minus 1. Let me write it multiplicative. Let me finish writing. Multiplicatively independent units of infinite order. The abstract. So let me be a little bit more concrete than this. It says that. So this is, you can write every unit in OF cross in the following form. There's some roots of unity. Sorry, R. Times some U1 and 1. U, R being this sum of real embeddings, number of pairs of complex embeddings minus 1, and R, or and 1, and R. So every unit you can. So basically, there exists some sort of so-called fundamental units, U1 through UR, such that other units are just product of these, up to some power, up to some roots of unity. Let's maybe give you some examples to start. So for example, F equals Q joint root of 2. Okay? In this case, OF cross is equal to plus or minus root of 2 minus 1 to the n, or n all in. If you think about it, root of 2 minus 1 times root of 2 plus 1 is 2 minus 1 equals 1. So therefore, root of 2 minus 1 is a unit. Its inverse is inside of OF. In this case, because OF is the adjoint root of 2. So root of 2 minus 1 is a unit. Its inverse is in there. And all other units are actually powers of root of 2 minus 1. Plus minus. So this root of 2 minus 1 is called the fundamental unit. You know what? And the general situation is that this group of units is equal to some sort of roots of unity, and then the rest is going to be sort of product of some particular fundamental units. And those fundamental units, there are precisely R of them, where R is equal to R1 plus R2 minus 1. So in my case, I have a real quadratic field. So there are two real embeddings. There are no complex embeddings. So therefore, R equals to R1 plus R2 minus 1, which is 1. So you have one generator in this case. Maybe I'll give it another example. This will be interaction. So I can do. So Keys was very helpful to give me this. So you have this. So this is degree 4 extension. So what are the embeddings? So this embeddings, fourth root 2 can go to fourth root 2, or negative fourth root 2, or I times fourth root 2, or negative I times fourth root 2, right? So you have these two are, the first two is going to, these two are going to real embeddings. So these are a pair of complex pair. And this real one, so there are basically two real embeddings and one pair of complex embeddings. And then what you should be expecting is that R should be equal to R1 plus R2 minus 1. Or in my case, it's going to be 2. And have this as an exercise. I don't remember the number. Right. Yeah. So, sorry. So in this case, I think this is equal to, but I'm not sure. Completely. So this u is going to be plus or minus 1 because you have. Alright, so it's just basically plus minus. Times the following. So you have 2 zeros. Because I guess this f contains the previous one. So any unit in the previous case will continue to be a unit over here. So anything which is look at root of 2 minus 1 powers, you're going to be a unit here. Because this contains the previous one. And you have something new. You can do fourth root. Well, you can do minus 1 this time. First root of 2 plus 1. I think this is equal. If it's not equal, then it's off by a small number. I really don't. I didn't prepare this, sorry. But you figure that more examples should be good.
Excuse me? So, how did we know that root 2 minus 1 is a fundamental unit in the first case?
Pardon me?
How did we know that root 2 minus 1 is a fundamental unit in the first case, in Q root 2?
It looks pretty small. I can't think of another number which looks smaller than that. It's not a, in general, it's a difficult thing to determine whether a number is a fundamental unit or not.
Okay.
It requires some calculation. But in this case, it seems to be if you're not believed, you can say, okay, a plus b root of 2 to some power equals to, say, root of 2 plus 1. This is the inverse of that.
Right.
I think it's unlikely you can find another number a and b smaller than 1 and 1 so that it works. So, yeah, this is the smallest one you can look at. And for this real quadratic case, there's a good algorithm to compute the fundamental unit. I won't have to attempt to just use continuous fractions to calculate the fundamental units in this case. But not now. Okay?
Also, in the second case, there should be some way to incorporate complex numbers. I is also a root of unity.
How should I put this? So this is a field. If you want to say complex numbers, you're really specifying, what it means. You're really embedding your f into it. You choose an embedding already, right? So here I wrote first root of 2, and some of the embedding will become the real number, and then some of the embedding will become the complex numbers. So if that's what you're thinking, right? It does not make. A priori, it doesn't make sense to say, an element in the number field whether it's complex or not. That would not make sense unless you embed it, specify embedding. Other questions? Yes.
Is there on the square? Well, you have a square root of 2 minus 1 in the last line. Is that supposed to be a square root or a fourth root?
Oh, maybe it's minus. You're saying
The very last line. Is this square root of 2 minus 1?
Force feature.
This is what the LMDB has, LMFDB has, in case you...
Maybe it is negative. Let's just be sure. Just to be safe. Just to be safe.
That was correct on the LMFDB, so this is correct.
What you have?
Oh, I guess you have one, you gotta get the other one. Anyways.
The plus or minus sign doesn't matter.
Yeah. Well, my question is 4 versus the square root.
Yeah, that's the square roots because the first one's contained in it.
Okay.
Sorry, what? I didn't quite get it.
No questions. Everything's fine.
Okay. But you can take n to be 0, that's what you're saying? Or... anyways, we can discuss it later, sorry. Other questions? Good. So anyway, so this is somehow something I hope you kind of get a good sense of, like the group of units, what it looks like. Okay. One of the typical applications of this is to so-called House equation. Oh, I should say, sorry. Before that, where's my theorem? There we go. Sorry. So this theorem, I wrote here OF cross, right? The same works if I replace this OF cross by Z of alpha cross for any alpha algebraic integer. So this works for Z alpha cross too. But of course, you're going to get a different generator, a little bit different generators. So as long as somehow this thing in OF is some sort of finite index stuff, it's okay. So somehow this group, I guess the general group structure of OF cross is not that sensitive to this finite index thing, because basically after all this looks like Z to the R times roots of unity called mu f. The roots of unity. Yeah. So it's a free group order of rank R. If you change a free group of rank R by some finite index, it was still going to be a free group of rank R. Okay. So application. For application, I'll talk about the Peltier really quickly. I will not tell you how to explicitly construct a bundle unit, but I just want to kind of mention that what we're doing is sort of interesting. I want to take D to be square free. So Pelt's equation. So he studied this equation back in, I don't know, long time ago. And of course, in a modern point of view, what this is saying is that you first of all kind of factor this as, oh, I'm sorry. He told me to write y root of, I think really. Okay? And if you think about it more, it's really just same as, let me recall how we define the units, right? The units are, those elements OF which are invertible, and those are the same as those elements OF whose norm is plus or minus 1. So finding this basically the same as, well, pretty much the same as, almost maybe, same as finding OF cross for F equal to Q joint root of D. Or rather, maybe finding units in here. Then by Dirichlet theorem, as I said, that this you don't have, even if D is common with 1 mod 4, you don't have to consider Z adjoint D plus 1 over 2. You can just say this. And there's some fundamental unit. It's called the fundamental unit. Okay? But of course, if you write this gamma 0 as some sort of x0 plus root of d, y0 root of d, then you know that norm of it in this case x squared minus dy0 squared is equal to plus or minus 1. I mean, somehow you don't quite know whether it's going to be plus or minus 1 a priori. So if it's like, say that if this can happen that x squared minus dy squared is equal to negative 1. But if that's the case, I can consider the square of the fundamental 0. You just write it there. I mean, you take a square and you combine the terms. And then say x squared is a fundamental solution. Basically, if you have something which solves the negative 1 House equation, just square the solution, you can definitely solve the House equation. So the general solution to House equation comes from, you basically have the fundamental solution here, and you raise to r power. And I mean, basically, you write it as xr plus. I should call it x1. I should start calling it x1. Sorry. Too late to go change it. So xr y. So this is a solution. And sometimes the Pell's equation has a good structure that if you know one fundamental solution, you can get the rest of the solutions. So, of course, Pell at that time didn't know anything about algebraic number field. He just somehow observed this factorization and makes the calculation. Let me give a really quick example. 5 minutes. In this case, OF equals to Z adjoint 10. And you can trust me that in this case, gamma is, the minimal solution you see is 3 plus root of 10. And the coefficient looks very small. And when the coefficient looks small, you're sure it's probably going to be the fundamental solution. That's my spirit. You can take norm of gamma. This is 9 minus 10. Negative 1. So it's a bit annoying, so you have to take the square of this. To get 19 plus 2, what am I writing? 6. So fundamental solution is 19 and 6. And the rest are somehow more. If you want to get another solution, you have to do 19 plus 6 root of 10 square or cube. You wrote down cube. How did I do this? For example, you get a very crazy solution. So therefore, this and x equals that and y equals that is the solution to the Pell's equation. 2 minus x squared minus 10y squared. So from a small solution, you can generate more and more general solutions. Okay? Other questions about this? Yes?
Is the R that you have above the same R that comes from the number of embeddings?
Oh, very good question. No, not the
Okay.
same thing.
All right. So we can just pick that R to be whatever number we want.
Yeah, whatever
makes
better
perfect
you
sense.
want.
Okay.
Yes. What's the Alma? It's always a good Maybe I'll use that. I don't know.
I just wondered why we were cubing it if there was only.
Yeah, no. There's no reason.
Okay.
I can do square, but square sounds a little too small. nothing special. Okay. So here's this is something from Wikipedia I printed. It gives you kind of the fundamental solution to this Pell's equation, where I guess his n is 9d. And x, y are the x, y's. So see, the numbers are kind of very jumpy. It changes a lot. This is something I want to say that although the n could be very small, but the first unit could be very complicated. The best way to get these fundamental units is by the method of continuous fractions. Right, root of n as continuous fraction, and then you unwind the process. So this is something I wanted to just point out. The unit could be large. Basically, have not much time, so maybe I'll just talk about one last thing about how to visualize these units, which might be interesting. Okay, how to visualize. So remember, so I'll just do one example. Let's do f equals q equals root of 10, which I did with.
Can you move the sheet down?
Oh, yes.
Thank you.
Not that problem. Thank you. Forgot about this. So in the past, when we talk about ideals, I want to embed f into r squared, right? But now if I actually do this, for units, remember that OF cross is basically all the elements U in O. And the norm of U is plus minus 1. Right? So that means that when I do the lattice in here, so what's the norm in this case? Well, if you have U equals X, X plus U equals X plus root of 10y. So unit really means X squared minus 10y squared equals 1 plus minus 1. So what is this? This looks like not quite a straight one, but sort of in this direction. It's a hyperbola. All the units lies on this hyperbola. So this is one unit 1, 1. Remember, this 1, 1 corresponds to number 1. And you have another. So this is where x squared minus 10. Oh, sorry. I'm sorry. This is not x. Sorry. Well, the norm of this equals this. So what is the norm of an element? So this x and y represent two embeddings of this. Sorry, I was wrong. So there are two embeddings. So basically the norm in this case is x, y. Just somehow, because this is going to be, the norm is just tau 1 of u, tau 2 of u. The way I coordinate my x and y's are, this is the first coordinate, this is the second coordinate. Okay? I'm really looking at a standard parabola where x times y equals plus minus 1. This is xy equals 1, and this is xy equals negative 1. And so this is number 1 here. And the next number is 3 plus root of 10, I remember correctly. So the coordinate will be 3 plus root of 10 and 3 minus root of 10. So 3 plus root of 10 here, and 3 minus root of 10. Root of 10 is like 3.16, so it's a little bit lower here. And then the next one will be kind of further down here. That will be 3 plus squared, and so on. If you think about this, it's not very convenient to see what they are. I know they rely on these two problems. But a better way to visualize is to take the log. And now, if I take the log coordinate, this is actually log of the x coordinate. I'm going to use, just write it like this. It's not the new x and new y. And what I'm saying is that log of 1, 1 is just really this point. So this is at this point. And where does this parabola go? So the condition xy equals 1 corresponds to log of x plus log or minus log of y equals to log of 1, which is 0. So in the log picture, everything will lie on this anti-diagonal line. And this point here will be, I think, will be x in direction is a little bit longer, so it's going to be here. So it's going to be log of 3 plus root of 10, comma negative log 3 plus root of 10. That's the same as log of absolute of 3 minus root of 10. And the next one is going to be equal distance, so it's the same distance. It's going to be point here and then go on here, and same for another direction. So I just want to say that if you want to visualize OF cross, it actually lies on a actual hyperplane in this coordinate, and they form a lattice in this hyperplane. I'm doing this for this case of a real quadratic field, but in general, OF cross will lie in some sort of r-dimensional space, but in fact it lies in some sort of hyperplane inside of here, and this becomes a lattice here. This is how you visualize the units, and you have some sort of lattice inside a hyperplane. And you can still talk about fundamental units. There's something called the regulator of the number field. That's also an important invariant of this number field. I guess I don't have much time to say other things, but hopefully Keith will say a little bit in the next lecture. I don't know what he has in mind. If he can say something, that's great. To how to relate these regulators and ideal class group with a special value of something, the L function. He talked about the original L functions, right? And there's a generalization of Riemann data function for number field too. How to relate these numbers with some special value of that, the generalization of data functions. Anyways, I'll end my lecture here, I guess.